Hi, my name is Tom Tal Thomas, and this is my lab report of Lab 4. This is the order of which I'm going to go through the lab report. The purpose of this lab is to determine the behavior of currents when resistors are in series and parallel, and the circuit's behavior when it has a capacitor in it, or an RC circuit. Some key results was that the protections were always matched the measurements from the lab for part 1 and part 2, and that the simulated RC time constant was 6.063. Some key principles are conservation of energy, which means energy is always conserved, can be created or destroyed, which leads to the node rule that current in, like a branch, always equals to current out. The loop rule, the sum of all changes in voltage across the circuit is equal to 0. The Ohm's law, the voltage is equal to current times resistance, and you can manipulate it for whatever you're trying to solve for. The current in RC circuits is time dependent, and that capacitors, when not charged, will automatically start charging, and when fully charged, will act like a gap, so which makes the circuit act like an open circuit. And when the source is disconnected, it will start discharging until it is completely empty and will act like a wire with no resistance. This is a circuit diagram for part 1. In part 1, there was two 1.5 volt batteries, one 47 ohm resistor, 100 ohm resistor, and two ammeters. The prediction was that the measurement of the first ammeter and second ammeter will be the same, and it will equal to 0.0204 amps found through Ohm's law. It was measured to be 0.02 amps, but that's approximately right, as it would not show more decimals. If the ammeter was read backward, it would read negative 0.02 amps. The change in voltage for the first resistor is 0.96 volts. The change in voltage for the second resistor is 2.04 volts. This is the voltage graph. As you can see from A to B, it jumps in voltage as that's the voltage source. It decreases over the course of resistors. More over 100 ohm resistor, as it has more resistance, and voltage is proportional to resistance through Ohm's law. And through everything else, it is stays the same, as there is no resistance in those parts. In this part, one 9-volt battery was used, a 0.2 farad capacitor, one 10 ohm light bulb, and one 20 ohm light bulb. Shown in the picture is the diagram of the circuit that was used. The light bulbs were used interchangeably, and some observations were that the light bulb dims as the capacitor is charged, which makes sense as less current is going through it, but it's actually just being held up by the capacitor. And if we were to remove the battery, as talked about earlier, the capacitor will actually start discharging, which will light up the light bulb again. Part 3 had the same setup as part 2, except with a 30 ohm light bulb and a voltmeter measuring the voltage across the capacitor. In this part, the capacitor was being discharged after being fully charged, and over the course of 20 seconds, with a measurement being made of voltage every single second. The equation used in this analysis was that the natural log of delta V over delta V naught is equal to the negative T over RC. RC is also the time constant and is equal to the resistance times capacitance. Using that equation, it was found that the RC, or time constant, is equal to the inverse reciprocal of the slope of the log of V over V naught versus T. We found that the slope was negative 0.16493, set that equal to negative 1 over RC, and found that the RC is equal to 6.063, which is different than predicted, as resistance times capacitance in this instance was equal to 6, because 0.2 farads times 30 ohms. In this lab, an error would be even tracking error through the stopwatch. Obviously, I didn't get the exact voltage measured. The circuit is assumed to be ideal. For example, the resistance of wires is negligible, the resistance of the ammeter is negligible, and that the EMF is equal to the delta V capacitor plus delta V resistor. If this lab was done in real life and an actual ammeter was used, the real ammeter will have a small resistance, so the measured current will be smaller. And if the lab was done in real life with a real battery to charge a real capacitor with no resistor in the circuit, ideally it will be charged instantly. However, it would not happen because even wires have resistance.